Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this lecture series on foundations of cyber physical systems. So, if you remember in the last lecture we had been talking about this transfer function view. So, of the system. So, let us say if you see this picture you have Bs which is the feedback signal, right. Cs is the Laplace transformed output signal, R again is the Laplace transformed reference input function, and Es is of course this Rs minus Bs here, and G is the open loop gain, okay, and this is the open loop gain, assuming there is no controller and there is no output, and then assuming there is no controller and there is no feedback, and with feedback here from the output measurements we have the feedback loop gain or the actual controller here. Okay. So, as we can study this diagram and we can quickly write a control equation, I mean the equations which represent the interrelation between them. I think that is quite easy to figure out and you will find it in all standard control theory books here. Okay. Now, coming to a way of studying such transfer functions. So, this leads us to these concepts of poles and zeros which are very fundamental in the design of control systems and figuring out how the system response is typically going to look like. So, what really are these? So, the poles of a transfer function are the values of the Laplace transform variable that cause the transfer function to become infinite, and basically if you have a transfer function with a numerator and a denominator. So, the denominator considering that as a polynomial over the Laplace variable s, the roots of the denominator are the pole, and similarly if the roots of the numerator are the zeros, because if you set those as the values of s, the function will, the transfer function will evaluate to 0. So, for example, in this one if let us consider a transfer function s plus 2 by s plus 5. So, you have a pole at s equal to minus 5 and you have a 0 at s equal to. So, this is your location of pole, they are conventionally marked with a cross and the 0 is marked with a circle. So, s equal to minus 2 you have a 0. So, this is your s plane representation, right. Now, we will try to link up this idea of transfer function based system representation and how based on the standard text this standard test signals these systems create a time response and how those time responses depend on the location of the poles and zeros. We are going to look at this relationship right here. So, like we said that the output response has these components, the forced and the natural response here. So, let us look at the response that is expected here. So, you have this transfer function and you have this as a, as you can see it is a unit impulse input. If you want to verify here you have you have a unit step input 1 by s, right. So, let us see what do we expect here. So, if you do this thing that is so, this is what you have, the convolution in the time domain will become just a multiplication in the Laplacian domain here, right. So, you should be able to write this in this form, right, because s times 5 and here. So, if you see you are looking at this as your system, and if you try to see what is going to happen. So, this is your input which is the unit impulse, right. So, that is having an input pole here, right, and this is where you have the input system 0 and this is where you have the system pole. So, in this slide if you see we are considering what that there is this unit impulse which is being given as an input to this transfer function, right. So, effectively what you have is this in the Laplace domain, right. The unit impulse getting multiplied by the transfer function, because in the Laplace domain your convolution in the time domain effectively must be a Laplace function in a multiplication of this Laplace in the time domain, right. Sorry, or multiplication in the Laplace domain here. So, if we just transform it in this way, so this is what we can write, right. We are trying to create a separation between the two responses that are there. So, that with that objective, if you just write it like this, so you have this, you introduce a 5 here and here, and then if you see you can just separate it out like this, right. You have 5s plus 10 here, right, and you can write that as well 2s plus 5 plus this 3s, right. So, you have effectively 5s plus 10, right, and then what you will get is this independent form which is 2/5 2 by 5 by s, and the other is this 3 by 5 by s plus 5, right. Now, question is why we are doing this? Well, we are trying to write this multiplication in this specific form. So, that now if you take the Laplace inverse and come back to the time domain, you are able to separate it out, you are able to separate out the response with the time variant and time invariant parts, right. So, you get a 2 by 5 and you get a 3 by 5 times e to the power minus 5 t. So, this is your transient response, right, which will die down with time, and this is the part which will remain, right, and so that would be your steady state response here. So, based on this derivation we can just say that well we started with this system as a simple transfer function, we gave it a unit impulse unit step input, and based on that if I just do the multiplication in the Laplace domain and do these basic transformations and then come back to the time domain, we get a steady state input and a transient input here like that. And why we are doing this is, if you observe these values of the transient and steady state response, you can see that they are kind of being dictated by this location of the poles and zeros, because you see this location of the pole and the location of the zero is kind of dictating the value of the steady state and the transient response here, right. So, if we talk in a if we just use a further magnification here, look at the location of the pole. You can say that this is also determining how fast this transient response is going to die down, right, and how much damping should be there in the response. And it is also determining that, I mean, both of them together are determining that well what should be the value of the steady state response. So, I am trying to just impress upon you that how the location of the pole and zero are going to give you an idea that what should be your response for the transfer function. Okay. Now, with these basic ideas, let us start analyzing transfer functions from starting from the simplest cases. Let us start with the first order transfer function. So, we consider this first order transfer function 1 by s t, right, with a unit negative feedback, right. So, if you try to deduce the closed loop transfer function, so I mean so it would be something like this, right. So, C s by R s is this. Well, how this is coming, if you just want to figure it out, it is quite simple actually. So, here you have C s, right. So, the way it typically comes is exactly the way you can actually write the open loop the closed loop transfer function, the closed loop gain for this given the open loop gain G s. If you just apply that same method here, Yeah. So, by doing such standard manipulations, you can actually figure out what is the closed loop transfer function here, which should give you this, right. And this is a first order system, as you can see, because you have only I mean you are not having a second differentiation of x here, right. A second it is only the first differential, and that is why you only get the term S t when you do the Laplace transform here, right. So, that is the point, the power of s is 1, and so this is a first order system, and let us now try to see what would be its time response. So, if you just take R s to be let us say this unit impulse function, okay, delta t. So, then R s is then R t is the unit impulse, then R s is of course 1, and if I just evaluate C t in the time domain from 1 by S t plus 1, you take a inverse Laplace, all you get is this, right. So, 1 by t to the power minus t by capital T, right. So, that is what you have, and well, this u t should not be here, right. So, this is your response. You can see that it is like a capacitor discharge curve. It is starting from the amplitude 1 by t, it is exponentially decaying, right. So, that is about how you get a first order response, and that means in this case your transient response decays to 0 and the steady state response is 0 anyway, right. If you do a first order response, right. So, and then what will happen is, well, you will have this R s as 1 by s, right. So, effectively you will have a first order system which would be given by this function, right. So, this will evaluate to 1 here, the unit time, right. And then the transient response is given by this, and the steady state response is given by this, right. So, this is 1 of course, because it is the unit function here, right. So, what will happen is eventually the value will be 0 at t equal to 0, sorry, that at t equal to 0 the value will be 0, and with time when the transient will die out, the value will be 1. So, you are gradually increasing from the 0 value to this final value of 1 in the steady state, and the time required for that increase would be will be determined this value of t here, right. So, that is how we have this first order response curve, right. You see this is the slope of the curve, the initial slope, right, and that is 1 by this time constant, let us call it a, right. And we define this to be the time inside which you get to 63% of the final value. There is a good reason for doing that, we will see, okay. And then so that is the and based on this time constant, we can define several interesting quantities like rise time and settling time. So, let us see. So, the time required for the system's output or to decay to 37% of its initial value in this case, or the other way, in this case to rise to 63% of its final value is known as the time constant tau, okay. And it is nothing but, as you can see, the reason we talk about the time constant is it is basically the inverse of the slope of this line, okay. So, once we know the slope, we know that how much time by how much time it will decay to 37% in case of the unit step, or it will increase to 63% in case of the unit impulse, right. So, this is about the unit step. So, the time required for it to go from 0.9 to 1 to 0.9. So, one simple thing here. So, this is when we are talking to decay 37% of its initial value, that's what is your this is with respect to the unit impulse response, and when we talk about the unit step, you are coming up to 63% of the initial value, okay. So, this is with respect to the unit impulse here, and this is with respect to the unit step here. So, in that way when we talk about this, we have 63% of the final value and we are writing in another way, that is 37% of its initial value. So, I hope that is kind of clear here. Okay. So, if we continue from here, then we have the next important thing, which is rise time. Rise time means when the time inside which I get to this zone, that is within 90% of the final value, that is the time required for it to go from to this position, and it can be figured out that this rise time is nothing but 2.2 by A. Okay. So, when we are measuring rise time, we are talking about the time interval inside which it moves from 10% to the 90%, this thing. Okay. And this is related with the time constant A, with inverse of the time constant or the initial slope A given by this relation, that is 2.2 by A, and the time required to go inside 2% of its final value, that is what we call as the settling time. So, this is my settling time, we are considering a 2%, but in different books you can figure that well the settling time may have a 2% or a 10%, different specifications can be there. So, here if we take the definition with 2%, so it is saying that starting from 0, the time required inside which I have a guarantee that the first order system's response would go to 98% of the final value, or in other words within 2% of its final value. Okay. So, that is how it is, and this the important fun fact is all these values can be nicely related to the initial slope. So, you see the initial slope is A, which is inverse of the time constant, and the time constant defines the 63% rise time. Okay. So, this time constant, like we said, is 63% of the final value, and here we have the rise time, which is the time for going to from this 0.1 to 0.9 of the final value, and that is related to the initial slope like this, and this settling time, which is 2% of the final value from 0, the time required for that is related to the time constant in this way. Okay. So, the point is, if we can give a unit impulse or unit step, in this case it is a unit step, all these things are with respect to the unit step. So, if you give a unit step to this first order system, and if you can measure these times, you automatically get to know what is the transfer function, because you can know its slope and you can figure out what is t, and then you are done, you have identified the transfer function. Okay. Similarly, you can also do a ramp response of the first order system, and you can see that well what are the how the inverse Laplace equation will look like, and from that you can actually figure out what is the transient, what is the steady state, etc., etc. But the thing is, the first order systems are not stable with the ramp and parabolic input, because you can see how these functions are. We are covering that these things are a bit fast here, but it is easy to figure out that well if this is your input, it continuously rises and the system output will also keep on rising to an unbounded value here, right. These responses go on increasing even at an infinite amount of time, and but they are stable with unit step and impulse, because these responses have a bounded output, but the impulse does not have the steady state term that we saw. If you do the impulse, then it eventually unit impulse, then it was eventually dying down to 0, right. And hence for this reason the way that you typically study a first order system would be to give the unit step like we did here, right. And with unit step we had this well defined rise time, settling time and time constant, and also we had this nice looking curve, and we could actually take out these different measurements and we can do a system identification. So, fine, the next thing that comes is second order systems, and we can see that well for second order system we will consider the second power of s also in the equation. So, typically the second order system will be characterized by this kind of a transfer function. So, you have Cs by Rs which is given by this closed loop, right. So, this is the open loop gain here, and this is the closed loop function here. And here omega n is what we call the undamped natural frequency, that is the frequency of oscillation if we do not have damping, and the damping of the system is given by this zeta, right. All these things have got their physical meanings. For the space of time we will go a bit fast here, but you will get the details about all these things in any basic control theory book. Okay. Now, what we are interested in is to figure out how the location of poles and zeros vary for second order systems with respect to different possible values of undamped frequency and damped ratio. So, if you see, if you take the roots of the denominator and if you compute the poles, if you see the poles are located at this position minus zeta omega n plus minus omega n times zeta square minus 1. So, if you take zeta as 0, you have imaginary poles, a conjugate complex pole pair, imaginary pole pair. If you have zeta between 1 and 0, you have the complex conjugate poles which are located on the left hand plane, and if you have damping is 0, you will see that the system output is undamped with this natural frequency, that is omega n. That is why this term, so that is why I say that this is an undamped, this term is known as the undamped natural frequency, because it dictates the frequency of oscillations here. And if you have a damping value, then the damping is less than 1, you have an underdamped response which will look like this, and this is an undamped response because it is fully oscillating and the oscillation amplitudes are not decreasing. Of course, all these are step responses, and if you have zeta equal to 1, then the imaginary part vanishes and what you have is two poles located at the same position in the left half plane, that is minus zeta omega n. So, this is the response here, and it is the response of a critically damped system. As you can understand, for a system it is very difficult to set the values like this and get critical damping, but if you have damping value to be more than 1, then you have two poles on the real axis in the left half plane, and you have the response as an overdamped system. Even this you may not choose to use because this is a slow response, whereas this is a fast response, and when you design a control system you will like to have this kind of a response. So, this will be your target area of operation. So, if you plot all these curves together, here you have undamped, here you have underdamped, here you have critically damped, and here you have overdamped responses. Undamped, which you do not want to have because it is like unbounded oscillations. Underdamped, you see it is rising quickly and it is settling down. Critically damped, something that you want, but it is difficult to attain. Overdamped, there is no oscillation, but the time it is reaching the settling time, it may be, so it is not rising as fast as the underdamped situation. So, see, like we have discussed that we will like to have the underdamped situation because the response is fast and also eventually it becomes stable, unlike the other cases critically damped, difficult to attain, and overdamped the response is slow. So, if I want to be in the underdamped zone of my design, so what we will have is something like this, right. We will have the zeta value between 0 and 1, and we will have complex conjugate poles of the system which will be located at here and here, right. So, for them the real part is minus zeta omega n and the imaginary part is plus or minus j omega n times the square root of 1 minus zeta square. Okay. So, maybe we will stop here, and in the next lecture we will start right from here. Thanks for your attention.